I don't know. My camera is definitely in trouble, so you have to believe it's me.
I'd have to switch to Julio's computer, except you're in a different place at the moment.
Yeah, I'm at home today.
Oh well. So the invisible Marcelo came from mineral processing background and went and studied under Peter King at Utah. And I can see in the way he approaches problems a huge influence on Peter King's approach around understand the science as best you can and then apply it in mineral processing. So, he still has arguably one of, the best mineral processing book around, with liberation, 3D liberation modeling in it, comminution modeling or understanding from the fundamentals, rock fracture mechanics side. And that's really come through to Marcelo. So when I need rigor in what I'm doing, I go and refer to Marcelo to check I've got it right. So it's always enlightening to work with him. Came back from his PhD back down to Rio and set up the research group there. And very nice. I think you said it's over 20 years now, isn't it, Marcelo? You've been running.
Yeah, 25 years this year.
25 years.
In a month.
So that's a pretty solid career in building a group. Build a group up from scratch and have your own laboratories and everything. And a lot of students have come through Marcelo. So it had a really big educational impact around Brazil, but certainly beyond Brazil as well. And its reputation is all around there. And I saw you were highly ranked in the number 4 or something in the global rankings in mineral processes. Although there's some dodgy characters in those rankings as well, but I'll say you're a genuine one. So working with Marcelo in the GCC has been really fantastic. I was set up to meet him by Walter Valery, and so I keep forgetting, but I think it was in 2008. We met in Falmouth at an MEI conference, and have been firm associates and friends since then. So Marcelo is going to share a few pearls of his knowledge and his wisdom and his experience with us tonight, or this morning, depending where you are. So over to you, Marcelo.
Thanks a lot, Malcolm, for the very nice introduction. But indeed, it's been quite a while that we have been working together. So thanks a lot for that introduction. Indeed, so it's been 25 years now that I'm in Rio. So it's amazing how time goes by. So thanks a lot. So sorry, my camera is not. It looks like it's on here, but it doesn't seem like you're seeing me. So apologies for that. So, but I hope you're seeing my screen, which is really the important thing, correct? So today we'll be talking to you about some of the work on advances in HPGR technology that I briefly review, but mostly I'll look at the HPGR modeling work that we have been doing. So as Malcolm said, I started this laboratory of mineral technology in the University of Rio de Janeiro in Brazil, and of course, quite proud founding member of the GCC. But I'll be speaking today on behalf of definitely a very strong group of people here who have been working with me on this topic for quite a few years now, which is made up of Tulio, here, Victor, Gabriel, and also Andres. Well, just briefly today, in the next 40 minutes or so, I'll just briefly talk about some of the recent advances in the HPGR technology that have been really keeping us excited. And then move on talking phenological modeling. One approach, which is that we have been really pursuing a lot in the last 2 years. And then move on to talking about how we understand DM as a fantastic tool to getting depth on the HPGR and move on to the conclusions. Of course, I think the group here is quite is quite expert on comminution, but just in case there's any newcomer, I think the HPGR has been arguably the most important advance in the field of comminution in the last 40 years or so. And of course, it was the result of the development of Professor Klaus Schronet in Germany. And the beauty of the system is that he understood that you can actually get fairly good efficiency if you actually press particles in beds under fairly high pressures. And this was conceptualized in a machine that essentially has two counter-rotating rolls that are driven separately by those motors. And one of the rolls is able to actually move or float over this frame. And the floating is the result actually of the pressurizing system made up of the pistons connected to the hydraulic pneumatic system with the nitrogen accumulator. So the beauty of the system is that you actually pressurize the bed, but it's able to actually move closing and opening to responding to the changes in material compliance here, and also the setup that you prefer in your system as far as pressures and so on. So there's definitely been a huge success in the technology over many, many years. And if you look at that picture that we have seen quite a while, of course, it's not in here the cement applications, which are quite significant until now, which started early in the 80s. But when you look at the mineral processing industry, we can acknowledge that the guys from Kimberlites or Diamond Doors, they took up the technology very nicely, mostly because of its ability to just pressurize on the soft Kimberlite material and leave the diamonds unbroken. But it took a little bit of time until it really picked up in the iron ore industry. But it did pick up quite strongly since then, especially in pellet feed preparation, as we'll be talking about. But since then, also in crushing applications for iron ores. What really is quite interesting is to see that outlying point when you look at the hard rocks. So in 92, 93, there was an original application of the HPGR, and that happened in Cypress, Florida in the United States. And it was exactly when I was doing my PhD in Utah that this was introduced. What happens that, well, what explains this such a huge lag between this and the actual successful second application there? It's exactly the fact that, unfortunately, it was not a huge success, mostly because of wear of the rollers that happened then, that resulted in very little availability of the machine. That really raised a red flag for the industry, which successfully was overcome only quite a few years later in Peru. But of course, since then, this has been increasing, and I think people even lost count because of the number of suppliers these days. But there's no question that everyone involved in a new project for a hard rock application, iron ore, definitely will consider HPGR in a trade-off study for any greenfield project. What made HPGR such a, I guess, a successful technology these days? I think there are some special features that really are quite particular to this technology. One, as I mentioned before, is the fact that interparticle breakage really is what happens there. So only a relatively small fraction of the particles that are fed to the machine that actually get in contact with the rollers. And so this really is quite an interesting aspect, because most of the particles actually are broken by other particles. Even though this is not as efficient as breaking particles one by one, it's definitely a much more viable option in terms of protecting the machine and its internal parts. The other aspect, which is quite important in the system that I just mentioned before, is the fact that it has this hydropneumatic system that really allows the movable roller to move back and forth and control the pressure that you want to apply to the bed. And this even it actually responds like a spring that you can actually make it stiffer or more compliant by selecting proper nitrogen pressures and the oil pressure in the system here. But of course, this introduces another level of complexity compared to an obvious simple roll crusher. The other aspect of the technology that was really part of this original design was the fact that it had to, since you had those pressurized rollers, you needed to contain the material from really spilling from the sides. And this was made up with the so-called cheek plates that are really consumable that eventually you have to replace. And this really was introduced to prevent this sharp drop in pressure close to the edges. But in fact, even with those cheek plates, we realized that close to the edges of the rolls, you really have very little size reduction. So very often, relatively often, people really even recycle edge products to the feed and really separate from the center product, which is definitely much finer. Some pilot scale work that we have done basically demonstrate this. When you look at the blade specific area for an iron ore pellet feed, it's quite clear that when you compare the feed blade size, which is about this, for 550 or so, when you compare to what really comes out of the machine, quite obviously close to the center, quite a lot of size reduction, but close to the edge, almost very little or almost none, depending on the conditions that you use. So that's something that was within the technology and has its features. But of course, as I mentioned, that I think the Cyprus Cerrito experience raised that red flag, meaning that wear would have to be taken care of if the HPGR was going to be successful in the minerals industry. And the result was definitely this very nice development, which is the proposed studded rolls, through which the tungsten carbide rolls studs here allow the material in between them to be built as an autogenous layer. So really prevents the roll itself from being worn too quickly and really extending the life quite fantastically of the rolls these days. And of course, there are other options like the Extruder, but not far as much use as the studded rolls. Yet another feature of the technology that was already built in the first design, what the allowance for the rolls to skew. So not only rolls are able to move back and forth in the X direction here, depending on the pressure that you apply, but also depending on the compliance of the bed, but also they were allowed to potentially move sideways. So basically, if you don't have skewing, and if you have problems with feeding your machine, for instance, if you feed coarse material to one side and fine to the other, if you feed much more material here one side and really starve the other, potentially if you didn't have skewing in your machine, potentially you have higher pressures in one side and lower in the other. In the long run, this will very likely result in uneven wear of the rollers, with much higher wear on the left and lower wear on the side. Of course, the idea is as segregation, you have to always take care of the problem in the root. But on the other hand, if you don't really do that, and if your rollers don't skew, eventually you will have uneven wear. The beauty of the technology, it was already considered from the start that you have to allow for skewing. So really, if there is an effect like this, what happens that the rolls will be able to compensate for this uneven pressure by moving sideways in such a way that the pressure will be slightly rectified here. So potentially it will give enough time to sort out the feed problems without really having to deal with severe uneven wear. Well, these are all features that I guess were responsible, at least in good part, for success of the machine in the early days, the technologies, so since the 1990s and so on. Well, the things that, of course, some interesting advances have been made since. Just want to really mention about three of them, which are the spring-loaded cheek plates, the rolled flanges, and the uneven rolls, which have been proposed in recent years as really a new kit to put in the HPGRs. I think the spring-loaded cheek plates have been proposed by Weir, today Weir. And the idea here is essentially to understand the cheek plates as things that can be managed. and not only wear as time goes by, but also closed as you need to make sure that you compensate for this wear. But of course, also be able to comply more with situations under more extreme skewing conditions, such as the one illustrated here. So by really being able to manage the cheek plates, you'll be able to potentially reduce this lateral extrusion, because if you, for instance, have very moist and fine feeds, such as the ones that we deal with in iron ore pellet feed, as high as 8% moisture, if you don't really have closed cheek plates, you have quite a significant proportion of material that can be just bypassing from the side of the roads and not really being reduced at all. So this is an interesting development, I'd say, recent, that can really improve the performance of the HPGRs. So another development that happened now quite a few years ago, proposed by Metso, are the row flanges. So essentially, this one of the rows are in input flanges in both edges, so that really it works like a moving cheek plate system, but essentially it's like this that allows these lateral areas to be more confined than you get with a traditional cheek plate. So the idea in this system is that to potentially reduce the edge effect, and also by reducing the friction between the cheek plate and the bed, you'll be able to also move more material through the rows, which is essentially increased throughput. So these are the claims, and some of the results already show that. Yet, just one last advance that I like to mention about is one fairly different design of HPGR that has been proposed, which is called the Argo mill. Essentially, this that is showed here from one company in Germany, that's shown here, Argo IPS, is essentially those two rows are really in an angle, 30 degrees here. And the difference is also that they propose only to motorize one of the rows, the other one responds to the motion of the bed and the other row of this machine. As you can see here, that potentially it could work without having been choked. So really just with a small bed of material here. And besides, another claims that potentially it would allow working with much higher velocities. As you can see here, we look at y-axis the throughput and the x-axis the velocities. We know from experiences that as we increase the velocity beyond a certain level, you start to get slip in most HPGR designs. And it's actually claimed that Argo can actually prevent this from happening by using this system. So these are some of the things that have been out there. Some of them already have been uptaken by industry, some others not. But it really shows that the scene in HPGR technology has been quite alive and showing that the technology will really continue to have a place in the future. But of course, as people who want to understand and improve both the operation and design of HPGRs, we'd definitely like to understand how we can really put the performance of the machine inside a computer to be able to respond to what-if scenarios. So I'd like to understand how the HPGR operates. So by looking again at the machine and breaking up into different contributions, such as material characteristics here, on the upper side, the machine operating conditions that we can really play during operation directly or indirectly, and of course the design characteristics of the machine, all dimensions and characteristics of the hydropneumatic system. With all those things, we'd like to be able to predict with fairly good confidence what will happen in the machine. So, of course, when we look at the real world, we'd like to, as I mentioned just a few slides ago, want to look at things that do happen in real life, which is where the rows do wear during operation. So we want to be able to not only predict what happens when the rows are entirely new, but also as they are progressively worn. We want to be able to understand the confinement system, the different confinement systems, how they will respond in a particular operation. And also we would like to be able to include, describe the effect of skewing in the event it may actually appear. So it really, there are definitely different levels of complexity we'd like to tackle in our modeling approach. So how can we do that? Definitely, there's plenty of complexity in what I just mentioned. So the approach we use is essentially look at, we want to be able to understand how particles break, and we can do this very nicely from individual particles here, as you can see, a microcompression testing system that allows us to characterize the distribution of strengths of very fine particles, 100 microns, 50 microns or so. But we can go to piston die systems to also get some insights on how the material will respond, to be able to take that information into the HPGR. But in the end of the day, we want to be able to use whatever tools are out there to be able to predict what happens in the HPGR. So we looked at phenomenological models, population balance type models, to be able to provide results such as throughput, particle size, distribution of the product, and power, but also recognize that there are obvious limitations to population balance systems because they really lack quite a bit of understanding of the physics behind the machine. So we look at DEM as a potential tool to be able to incorporate quite a few complex things, such as details of the hydraulic system, skewing effects, roll, moving effects, and so on. So in order to do that, we coupled to Vale here in Brazil, who was really keen on improving their HPGRs. You can see here that their HPGRs are quite in the middle of the whole process for preparation, producing iron ore pellets. So really, they're downstream from traditional ball milling classification steps, and they are upstream from the pelletizing operation. So they're basically the last resort that you have to still add value to the material before they become really commercial products, which is iron ore pellets. So the HPGRs have a role there, and they have been used, as you have seen the last few slides, quite successfully, a number of units around the world and Vale since the 90s. But when we started to talk to them, we realized that the level of understanding of the performance of the machine was relatively limited for this application, which is definitely not the application that we see these days, and definitely not the application that originally brought HPGR to industry, which is cement, which is quite a dry material. So we did sink our teeth into the phenological modeling world, and back then we saw essentially three fairly successful approaches that have been proposed in the last couple of decades, which is of course, the traditional model from the JK, and Torres and Casale from Chile, and of course our good friends from the GCC in Machu led by Hakan Benzel, another approach. So three successful approaches that essentially incorporated most of these variables that you can see here, material variables, machine settings, and really calculated or assumed key variables such as gap and considered pressure, and gave some of these outputs. Some models did provide some of them, others not all of them. What we did do is basically because of our experiences, as Malcolm mentioned, I did my PhD in Utah, and a lot of the work from John Herbst and the energy-specific selection function was done there. We could see really the potential of this Torres and Casale model to be able to give a good contribution to that application that we're interested in, which is iron ore pellet feed. So we really invested quite a bit of effort improving understanding this model and how it can be applied successfully to HPGRs grinding pellet feed. So just the overall the overlook of the model essentially is that the population balance model is used in that, and it's assumed a parabolic power profile, and on the basis of the machine settings, the material variables, and some key variables such as gap, the model assumed plug flow to predict throughput and assume just a simple power equation on the basis of compression, compressive force, and nip angle to be able to predict power. With power and throughput, we could definitely calculate the particle size distribution. This is the original Torres and Casale model that was proposed quite a few years back. Well, it's documented in quite a few publications that on the basis of extensive data from pilot scale and industrial scale, we actually understood that in order to be able to apply successfully this model, we needed to modify. So we called it modified Torres and Casale model, by actually understanding that the nip angle is really a parameter that has to be fitted on the basis of good data. We understood that the breakage of these materials were fairly unusual, so we updated the breakage function. We incorporated the effect of saturation. We also understood that depending on the design of the HPGR, the parabolic power profile doesn't appear, but rather the trapezoidal one. So all those things, including material acceleration, material ejected from the edge of the lows, were all introduced to be able to, for the model to describe reality. So essentially what I just mentioned is that when we naively apply the Torres-Casale model to data from pilot scale and industrial mills, we could essentially see, basically these are industrial HPGRs, we could see that the quite a big difference between the experimental and the predictions in the model. What we did then is incorporate those effects that I just mentioned, the effect of edge material being ejected from the edge of the rows, as you can see illustrated here, that we can see in practice quite a significant in HPGR with aromatic pellet feed, effects of acceleration and so on. With all of those effects accounted for, we could actually get very good predictions of throughput with this model. So definitely ejected material played an important role, and we could map this quite nicely as a function of speed and a few variables, as you can see here. On the other hand, when we look at the power prediction, actually it was essentially very good agreement, just with a bias here. So the experimental and calculated were quite different, but nevertheless, just with a bias that could be corrected, essentially by introducing a parameter that is adjusting the nip angle from the calculated one. So also, just by doing this tweak, we could actually get very good prediction of power for a range of machines from industrial pilot to industrial scale. And when we look at the breakage model, we, as I mentioned, we actually incorporated the effect of a normalizable breakage function. So this is a breakage function that has yet another term that allows to tweak the size distribution of the product that you can see is required for materials such as aromatic pellet feed. And the result is that we got fairly good agreement between the experimental and the predicted blame results. But yet we could see that for very high pressures such as these, we realize that we are overestimating the blame of the product. So it definitely suggested that we are not taking care of something important here. And that's exactly on the basis of piston and die data that we collected from the lab. We could see that there is an inefficiency that appears as you increase the specific energy or the pressure. So by introducing this correction for inefficiency due to definitely overloading energies, you could actually get much better agreement between the predicted and the measured blame specific energy. So in addition to that, the original model by Torres and Casale assumed the parabolic power profile. But in fact, when we look at industrial machines, we see very often this more or less trapezoidal size or power profile. So by actually, we incorporated a different model here, which allows us with just a single parameter to predict, to describe this power profile, which actually translates into like a fineness in the product profile that you can see here in the black line. So also we were able to very successfully describe that both from pilot and industrial scale machines. Of course, I think these, when we talk about the model, we have been using in minerals industry quite a lot offline, so to improve the process and so on. But we'd like to definitely use this model now to make decisions online and to assist operation. So this really requires to make, to do another view of the model, which is exactly look at real-time information on the process. Understand that if you want to predict operation in an HPGR, where will have to somehow be understood. And in the case of iron ore pellet, you have to account for the fact that you're blending materials in the feed with time, and that blend changes. So potentially we can use this type of information with the model that we develop. It's essentially a quasi-dynamic model, because it's really, we're looking not at very short dynamics like within seconds, but really looking at dynamics within minutes and hours. So the vision that we have is to use the model that I just showed to you as a digital assistant, as something that can be an assistant to the operator to understand what lies ahead in the next few hours of operation, to be able to better fine-tune the operation instead of really just responding to whatever happens like in typical control systems today. So potentially this approach can be used also as a control strategy in the future to improve operation of the machine. So how did we go by testing this model in using real plant data? Essentially here, just looking at the very short time spans, we actually, you can see the yellow lines here. A yellow line is essentially the data from the plant, from the supervisory system, and on the basis of data that we have from the feed and the settings that were used, we could actually essentially predict the throughput fairly well in a very short time span, and also predict the power, leading to fairly good predictions of the specific energy. The problem is that when we started to push our luck a little bit further, which is now looking at months, not a week or so, it became quite obvious that something else is happening, because our simulations were definitely doing a very good job in predicting throughput and predicting power. Luckily, there is a tradition in the plant to actually measure the profile, and we can definitely see here that in the beginning, of course, the rows are fairly new, so things are all well. But as time goes by, we could see that there is progressive wear of the roads until very extensive wear here. And this, we understood it was the reason why the model was already completely failing in predicting the operating condition, the outcomes of the process. So what we did is actually put together now allows to fine-tune a couple of model parameters, very few model parameters that we call F1 are here and F2, to be able to account for just a tweak in the throughput and a tweak in the power, to be able to predict the results from operation. So just by doing this, we could actually reduce quite dramatically the deviations from the model to what we see in practice as far as throughput and power. And of course, the result by doing this, we could see very good prediction here in specific energy for a short term that we're already doing a good job, but especially for a very long term, maybe over a year. So over 2 years in operation. So we're definitely very happy to be able to do that offline, but using data online. And just to illustrate, we want to be able to use this information to let them know what they could have been done differently in the operation. So for instance, when we look at the feed to the HPGR, the blend, which represents finance, varies quite a lot. And what we have seen in practice is that the product of the HPGR is almost responding to these changes in the feed. So it means that very little is done these days to tweak the HPGR to actually try to get what we would get, which it would like, which is essentially a constant blame for the pelletizing operation. So essentially, first what we did is just apply the model and to say what would be the prediction of the blame. It's fairly good. It's not really as close, very close to the product, but gets very nice the trends. So we qualified, I believe, to be able to propose to them, what they could have done differently in the operation. So in able to demonstrate that, we'd like to show what could we do if we actually use the model to optimize these operations. So these are the same data as before. So by doing this, we could essentially say that if we tweak the velocity and the pressure using the understanding from the model, we potentially could get this level of constants in the blended product, which is far dramatically less than what we see in practice. As you can see here, deviation as 13.6 compared to 66 centimeters square per gram. So, and throughput, of course, we could actually drive throughput to very constant value of 600 ton an hour, which is exactly what they need in the pelletizing operation. But of course, this is important to see that in practice, this would require much more significant changes in things such as pressure and velocity. And what we see in practice that the operation ends up being very conservative, keeping the pressure and the velocities almost constant, even though there's quite a few things changing, such as the feed characteristics and the row characteristics. So we believe that the model will be able to allow people to definitely look outside the box of operating conditions, because all of these changes here in the black predicted are well within the conditions that can be dealt with in the machine. So by using this, we could demonstrate that they could reduce as much as 5.8% in specific energy and get a much more constant product if they actually have these two online. So, and on top of that, if you look at this specific energy utilization, which is essentially specific area per kilowatt hour per ton, we could demonstrate that by operating optimally the HPGR, we could actually increase the efficiency by as much as 19%. So these, I think we're happy that we could demonstrate this application of the phonological model, but we do realize that we needed to go through some empirical changes there in the model to be able to cope with reality. Even though we know the explaining things, for instance, are where things that we can actually measure and we could incorporate this understanding in more detailed descriptions. So these really motivated us to look at DEM as a very powerful tool to simulate the HPGR. But I think the answer to the question is that can we use DEM right away to simulate the HPGR? I think that the answer is not really. DEM alone cannot really describe what happens in the HPGR. The reason are at least three. The first is the fact that you really have to describe the multi-body dynamics. So you have to describe the fact that, one of the rows are moving, responding to the compliance of the bed. So we have actually been able, together with guys from DEM Solutions back then, Alter DEM, to incorporate this model into EDEM since then, and it's already standard today. And very recently, we have even been able to not only put the motion in the X direction, but also the twist XY direction here to be able to get this queuing described. The other piece of the puzzle that is required to describe HPGR operation DEM is to be able to actually break the particles inside the environment. So this was done using a particle replacement model that we actually implemented in the code a few years back. And this breakage is fairly detailed because it accounts for the distribution of particle strengths or breakage probability, variation of particle strength with size, energy-dependent fragment distribution, and the damage that results from speed stressing. Even though this model was originally developed for impact, we have been using this for compressive systems fairly successfully with just some challenges that I'll just be talking to you shortly about. And so how did we go by using this model? So we first did quite a bit of validation work on the basis of piston die testing, material calibration for DEM, contact parameters, and using extensive data for pilot scale machines. You can see here the throughputs in the tens of thousands of tons an hour. And you can see here, just a little bit of fine tuning in the DEM, we could actually predict on the basis of just one test results from a number of different conditions, which is velocities, pressures, and this applies to throughput and power. So we can actually get those two from the DEM simulation fairly successfully already with just one base case. And of course, the beauty of DEM is that you can really go inside the machine and understand some of the details. For instance, you can look at the pressure force distributions just right at the gap, as you can see here, for instance, or almost the gap as one, and then see that is if you move upwards, of course, the force is reduced quite dramatically, but you may also get some breakage. And it allows us to exactly see the nipping when it happens in the HPGR compared to what you see from the equations here. So one of the things that we can do in DEM is answer the question, what happens when the rows are worn or partially worn? So in that case, we have seen in HPGRs two different profiles develop. One is the so-called parabolic profile, which is exaggerated here just for you to see. So it's very essentially a parabolic wave profile here, higher at the middle, lower at the edges, and here more like trapezoidal profile here. And so just by really looking in the case of both of the HPGR brand new, this is the force distribution that you have. As you know, you have seen before, lower pressures in the edge result in lower forces, low forces here, more or less average in the middle. And so this is what you get when the HPGR is brand new. What you can see here from those other lines is that when you actually have different profiles such as these, there is quite a significant drop in pressure in the middle of the HPGR, because of course there's a gap here that increases in relative to the edge, and there is a peak that appears close to the edge here, which is essentially because it's an area that was not originally solicited very much. So this is the type of complete change in the profile of the machine that you are expected to have as you get the HPGR award. Other thing that we could study using simulation is the effect of segregation in the feed. So for instance, if you have segregation in respect to feeding, for instance, one part of the machine is fed very strongly with material and the other is underfed. One side of the machine is fed with coarse material and the other with fines. One side of the machine with very tough material and the other with very soft material. What happens in the degree of skewing? So skewing, as you know, it's in millimeters per meter of the rows that is measured. And here is the relative variation in all those things, throughput, size, and strength. You can very nicely see here, of course, if there's no variation, there's almost no skew. Here is just a amount of 0.5 millimeters skew. But as you get more and more variation, especially here, if you have segregated feed, coarse material on one side and fine on the other, very little segregation in respect to size leads to very significant skewing, 4 millimeters, almost 5 millimeters per meter. So it's a little more compliant here. If you really have strength variability, it doesn't really skew as much. So these is some things that we can really look in simulation and of course, look back at operation and check if it makes sense. Of course, the pellet feed material that we deal with is extremely fine. So unfortunately, one huge challenge that we have is to get size distributions to match what we can see. So qualitatively, you can see here in the simulations and the predictions, we can have pretty much the same profile when you look at the radial samples that we get from the HPGR pilot scale. But quantitatively, you can see that definitely we over predict the coarseness of material, so we cannot really match what we can see in practice. So you can see here that definitely when we look at the 80% passing material or the passing 45 microns, for instance, it is quite off what we can see, what we measure experimentally, but nevertheless quite consistent with the predictions, at least qualitatively. So just very quickly in the last few slides, since I talked a little bit about some of the advances that have been happening in the HPGR technology, I think it's interesting to see that what happens if you actually implement some of those changes in your existing HPGR. That's typically fairly expensive to answer if you want to do in the real life, but I think this is perfect to be done in DEM because, for instance, we can see what happens if you put spring-loaded cheek plates in an HPGR that just have regular cheek plates. So if you have regular cheek plates, what you see is something like this in an HPGR. We have material flowing, the mass flow material in the middle, fairly constant, but then it really raises close to the edges when the cheek plates are new, nicely closed for a standard operating condition here. But that's very nice. But then what happens is that due to wear, you start really having more and more allowance of material to spill from the sides of the HPGR. So what happens is that even drops a little bit the flow from the middle because some material will be spilling out from the edges and obviously material that will be pressed very little. That's something that you don't want in an HPGR, but happens in practice because the cheek plates are being worn. What happens is that now we could simulate the effect of doing exactly what the spring-loaded cheek plates does, which is apply a force here to make sure that the cheek plates keep closing, even though they are getting worn, as you can see here. And by doing this, you can see in red here that you fairly compensate the wear by actually pressing the cheek plates. So the mass flow and the can be really reduced. When you look at the details, for instance, what happens when the HPGR was new and compared to what happens when it's actually with the spring system is applied, you can actually compensate quite a lot because we reduce the bypass that increased because of wear and basically even retain essentially the throughput before. Doing worn rows, of course, you have much throughput, but you don't have much size reduction. This, you can even see here that depending on the conditions, you can even increase power if you actually push the spring even further, and the specific energy can be pretty much managed to the level that you want, whereas in practice, it will reduce if you don't do anything and if you just allow the rows to wear. Other application that is feasible to study here is the flanges. So we know that if you have an HPGR with cheek plates like this, we can actually put flanges. Those flanges can be even smooth flanges or pin flanges, as you can see here in the picture. And we'd like to essentially see what happens if you actually input flanges to an existing machine. So this is the original design, the throughput here, the mass flow rate, as shown before, some material spilling from the sides because of the distance from the cheek plates. What happens is that if you put smooth flanges, you can see, actually the distance difference was very, very modest, meaning that depending on the configuration of the flanges, if there's no grip that really can be exercised by the flanges, you may not really see much benefit. On the other hand, by putting studded flanges, you can see here, it definitely reduces variation in the flow rate from the edges. So reduces this material spilling from the sides. It definitely seems like a good thing to have in the HPGR, which indeed it is, because you can see here the blue line, the force distribution, exactly more like a parabolic profile, whereas you can see here the studded flanges may manage to really get the forces more or less average across the whole road. Of course, there's still the edge effect, but definitely much more reduced. So when we look at numbers here, it is interesting to see that, yes, we could actually, for instance, looking at the cheek plate simulation, we get results here, for instance, 30 tons an hour with a specific energy of 2 kilowatt-hours per ton. When you actually put the studded flanges, it changes quite a bit the gap under exactly the same operating conditions, but of course increase the throughput and increase power. But on the other hand, it actually reduced a little bit the specific energy. So it actually is important to have in mind that if you put flanges, you increase probably the throughput, but it's important to see if you have enough power to cope with that. Otherwise, you will probably have to work with lower velocities. to keep the same product size reduction. Of course, here you can see here from the experimental data to the simulation, there's obviously a big difference because of the fact that we couldn't put enough fine particles, but nevertheless, we believe that these trends in the simulations are reasonable, which is when you put studded flanges, you don't really change conditions, you really reduce the specific energy, so the product will get slightly coarser, even though more uniform. So very last thing that I'd like to talk about is that Argo design, which I call uneven rows, which essentially are the rows that are really at an angle. We did exactly that simulation for that system. Remember that it's not a choke fat crusher row HPGR anymore. So we simulated that for exactly these conditions here. And the result, remember that one of the things that really are highlights for the technology is the potential to work at higher velocities without really slipping. And well, what we did see using exactly the same data as before for the other HPGR is that, well, we couldn't really see this effect at fairly high velocities, 2 meters per second. So the throughput actually compared to the traditional design was lower, and the power was actually lower. So of course, the specific energy was higher, but definitely didn't show this trend that we observed here. So it is something that is really worthwhile looking in more detail into this technology, because at the first test, I think we couldn't really verify. Because in fact, what happens is that since one of the rollers are actually driven and the other one is responding, it ends up to have really quite a bit of slip in one of them in comparison to the other one that is driving. So in top of that, the force distribution along the rows is quite different from what you get from the normal HPGR. And of course, the one that is driven here raises the forces, and the one over there ends up actually having more slip. Well, just final slide here, I guess, is to show that we have been working on hybrid modeling approaches, which is use the modified Torres and Casale model in conjunction with the DEM, because we see that DEM is quite powerful to be able to look outside the box that I just show you, to predict power and throughput, but not easy yet to predict with fidelity the product size distribution. So what we did is really use information from this HPGR simulation on the on DEM to be able, with the Torres and Casale modified model, to be able to predict what happens in the product size distribution. So these essentially were data from pilot scale that we could actually, using DEM, transform into predictions into a full-scale machine in North California. So this leads us to the conclusions, which is regarding the HPGR phenological model. I think it has the ability to describe, has been able to describe 4 industrial HPGRs operating under a range of conditions, under steady state conditions. But the real-time HPGR model has demonstrated to give very good responses to pressing iron ore concentrates in industrial scale, with potential application as a digital assistant to seek optimal operating conditions. Whereas DEM simulations really gave good predictions of throughput and power, and already I think it's a valid alternative to analyze HPGR performance under extreme conditions, wear, design, but of course we're quite busy. So regarding the phenological model, we're working on improving the model description of the saturation effect. We're looking at multi-component feeds and how the HPGR responds to that. Good work was done by our colleagues from Turkey on this topic. And whereas in the online model, we're looking at the improving description of the HPGR dealing with warm rows implementation, and we also were busy with implementing in industrial plant as a digital system, and we are already looking ahead as its potential to use in advanced control. Whereas the DEM, we're looking exactly at crushing applications, those applications that we can actually put coarse particles exactly as they live in the real world to be able to be predicted. So I'd like to thank my group here, different formations from a few years back, 20 years, and now last year. I think Malcolm is somewhere in the picture here. No, not sure, but he was in the party for sure. So thank you all for being present, and I'd like to be available to answer any questions that you might have. Thanks. Back to you, Malcolm.
Just wrestling with the, yeah. Okay, well done, Marcelo. Quite a far-reaching seminar as usual. People might not appreciate how much material is covered in that, the years of work, and how much at the cutting edge of rock breakage that work from. Really good example of bringing science, engineering, computational tools, and practical knowledge and application together, and not easy to do. So thanks, Marcelo. So, Grant, of course, has an instant question.
Shoot.
Hi, thanks, Marcelo. Really interesting question, really interesting presentation. I'm interested in the flange versus cheek plate design of the rolls. You talked about the fact that reduces the variance in pressure, increasing the pressure on the edges, but then also the increase in the operating gap. And I was just wondering if you can describe which one of those in your models was actually responsible for the increase in throughput, because it looked like the operating gap doubled, but the throughput didn't quite double. So yeah, I was just interested in what is actually creating that increase in dot and throughput.
Good point. Exactly. That's in some simulations, the difference in gap is quite significant. But nevertheless, it is important to see, even though I didn't show here in enough detail, that when you look at the throughput along the rows, that relatively big drop that most of the time happens close to the edges, actually the rows increase quite a lot. So it turns out that that the edge material that is really being able now to pull from the edges because of the flanges is important. But I'd say is a half and half contribution. As part of it is exactly the higher gap, but quite a significant part is the pull from the flanges. But I think it really depends on the grip of the material. So very dependent on the moisture and the friction that is dependent on material and design of the flanges as well. So I'd say keep an eye on the flange design.
Thanks.
See, Christopher has a question.
Yes, it was also a bit of a curiosity about the flanges and how they perform connected to with skewing. So do flanges like on the Mezzo HPGRs perform? Do they work with skewing as well, or are they just for rolls that are completely parallel?
Yes, definitely. Yeah, I think that definitely the challenge here is that if you want to be able to skew with flanges, you definitely end up missing part of the benefit, because you definitely have to leave enough freedom for them to roll. So I'd say that flanges, you can, I think there are designs these days that people are introducing flanges but allow skewing, but I think the extent of skewing, you have to have your system a little bit stiffer regarding this skewing effect. But if you can, and I think you should allow a little bit of skewing still to be used even with flanges, but of course not as significant, not as 5 millimeters per meter as you can see when you use cheek plates. So, but Maxwell definitely advocated that you have to stay away from skewing, period. I think it's skewing something like those, I don't know, like medicine and poison, that I think too much or too little is bad. So you have to really manage it to be on the right proportion.
Thank you. Great presentation
Thank
as well.
Yeah, there's some discussion in the literature between the Weir group and the Mezzo group on the advantages of skewing or not skewing. And it's quite interesting to see you pick those that play-off between the two when you look at it, you know, through the DM, that it's not obvious that there's always an advantage to a flange with zero skewing.
Indeed.
So the Met's original design would force a system that couldn't skew, but the updated one is quite different. I was quite stunned when I thought.
Yes. Since the arch frame was abandoned, I think you can still have skewing, but of course not as significant. But I definitely think that it's something that it doesn't mean that you have to leave skewing all the time. So you have to deal with the problem that's created skewing, but staying away completely from skewing, you're bound to have problems that you may not realize with an even way.
Any other questions on people's minds? I think kind of circling back to what I said at the end of Marcelo's presentation, hopefully brings an idea to both our academic side and our industry side, how you build a suite of tools to start assessing the questions. There's not one magic tool, because none of them answer all the questions, and really converging different phenomenological tools with more, call them mechanistic DM style tools with mechanistic breakage. You start gaining insights you couldn't have actually got another way. And I'm hoping to see these approaches really penetrate process modeling rather than the heavy reliance we have on empirical and phenomenological models currently. Well, thank you for joining us, everyone. Oh, I see Stephen's got a question. You're up, Stephen.
Yeah, hi. Hi. It's a bit late at night here, so I'm not going to put my video on. Apologies. But I had a question just about the piston die testing and whether you were able to determine enough information from a piston die test in terms of breakage to put into an HPGR operating machine to sort of predict performance from that.
Now, good, very good question. So I think what happens is exactly this, that in the piston die test, what we got, because of iron ore pellet feed is such a fine material, we actually focused mostly on the rheology of the material, how it responds to stresses, to be able to pick up that in the simulation and really tune some of the breakage parameters. But really, quite sincerely, the breakage in this was almost a qualitative description. So we couldn't fit the material breakage because it was really 100 micron materials, very fine. What we're doing right now is exactly addressing this, because now we're looking at crushing applications. So now the question is valid that you say that, well, do we get enough information from piston die? That's exactly what we're pursuing now. And in fact, that's exactly what we are improving the model to be able to cope with very high confinement systems to predict it accurately. So it is ongoing work to be able to predict size distributions with confidence without really going to unrealistic model parameters, because the model that I just showed to you is already out there in Rocky and in Eden, and some people have already been able to predict the product of an HPGR. But on the other hand, backfitting breakage parameters, we don't want to do that. As Malcolm said, that we want to be able to firm as much as possible on single particle, piston die, and then the HPGR. We have been able to do for other machines. HPGR now is exactly what we're doing, because now we're involved in crushing applications, not only this terrible fine size reduction in pellet feed.
Thank you very much.
Thanks, Stephen.
Okay, thanks, Stephen. Okay. Well, let's close off. Thanks for joining us. We'll have another one in a month's time. And I can't offhand remember the next one. Maybe Tulio knows. Oh, we haven't actually finalized, have we?
Yeah, we still need to define the next one.
We will finalize and we will invite you. Thanks for joining us. Great to see a good attendance for a great presentation.
Thank you very much, fellas, for that.
Cheers, everyone.
Thanks.
Thank you, Professor. Cheers.
Thanks all. Bye.
Thanks, fellas.
Thank you very much.